Welcome to the Chapter 6 lecture on volcanoes and volcanic hazards. The first box in your notes today is, what do you know about volcanoes? So based on what we talked about in last week's lecture and the week before that, rock types and plate tectonics, you already know that volcanoes are producing igneous rocks. You already know that they are associated with tectonic plate boundaries, and I'm sure you already have an idea of how they work based on your previous studies, based on the news, based on even watching disaster movies. We've all seen images of volcanoes before, so you already have an idea of what's coming. The point of today's lecture is to look at the different types of volcanoes that exist, emphasizing their style of eruptions, what sort of rocks they form, and what sort of landforms are created there. We want to look at volcanic hazards of different types of eruptions and past disasters. Also, we'll be looking into what are good methods for studying volcanoes and assessing the hazard of the volcanoes. The next box in your notes is checking out Mount St. Helens. So you've got three images there, before, during, and after. So if we look at my presentation, we're looking at a map. So we're looking at the Pacific Northwest. Mount St. Helens is being pointed out right there at the end of that white line, and this is in Washington State. So before the 1980 eruption, it looked like a nice big mountain, right? Very high elevation, lots of snow. So as far as your description before the eruption, if you were to say it is a snow-capped mountain, that would be spot on. During the eruption, what do you notice? So some things are very different here, right? Here's the top of our mountain. It has been basically pulverized and turned into ash and erupted up into the air. So you see lots of ash erupting into the atmosphere, and the top of the mountain is completely gone. Now if we take a look after the eruption, the main thing that you notice is, instead of that nice mountain peak, we have a big crater or hole where the mountaintop used to be. So that's the main thing I want you to notice there. The ash from this eruption rose 25 kilometers, and it spread across Washington, Idaho, and Montana. The lava dome in the center, if you look at that after shot, at the center of the crater you see a little bulge there. That's the lava dome, and that formed after the eruption. This volcano is constantly being monitored by the USGS to make sure that we can anticipate the next eruption. And luckily we had some warning before the previous eruption, so they were able to evacuate most of the people that were there. But as with most disasters, some people were stubborn and didn't move. So that's always an issue with volcanic hazards, is even if we can tell if something is going to erupt, it's difficult for people in the surrounding areas that maybe have lived there their entire lives to realize it's vital for them to get out of harm's way. And this is a new feature in the lectures this week. There's these little blue play buttons, and I've gone through and found quite a few really cool videos for you, and I hope that it will help you visualize what's going on in some of these photos. So this is a really neat video of the eruption of Mount St. Helens. Go ahead and click there and you can watch it. Alright, so what is and is not a volcano? Not every mountain is a volcano. and not every volcano must be a mountain. So, what are some common volcano characteristics is the question in your notes. So if we take a look at my slides, we need to have a vent where magma is being erupted. Okay, so when molten rock is below the surface, we call it magma. Once it reaches the surface, we call it lava. If it cools below the surface, so magma cools off and solidifies below the surface, that's an intrusive igneous rock. If it's erupted out as lava and cools, then we call that an extrusive igneous rock. Okay, but either way, in order for it to be a volcano, we have to have lava coming out in some way. It's got to have a vent. Okay, similarly, we should have some sort of crater. It can erupt lava or ash. It commonly forms a hill or a mountain, but it does not have to be a hill or a mountain. And it can be erupted from a fissure or depression, so not a hill. So it does not always have to be coming from a cone shape. Sometimes these big cracks in the ground open up and lava starts spilling out. So that's called a fissure. Or we can have a depression, which is it's kind of like a big crater that lava would be coming out of. So any of those are components of what we need for a volcano. So as far as your notes, you can write everything that's on the slide, or you could say a cone-shaped hill or mountain with a central vent from which lava, gases, and material are ejected. Okay, I'll say that one more time. A cone-shaped hill or mountain with a central vent from which gases, lava, and material are ejected. Alright, and so this last image here of the fissure takes us to the next page in your notes, and the first question there is: every hill capped by volcanic rock a volcano? Okay, well, let's see. We'll go to the next slide here and try and figure this out. We know from this last image here that we can have a fissure, which is not a mountain or a hill, but rather just a crack in the ground where lava is pouring out. So let's see, how does this fit in with this next page in your notes? Alright, here we go. We have in this first image a fissure, erupting lava all over the surface here. Okay, so again, a fissure is just a big crack in the ground that's being fed by magma below, and lava is spilling out. Okay, the next image is after the lava is done flowing, the rock has solidified, and now it is susceptible to erosion. So think back to the rock cycle. When we're in normal surface environments, we're dealing with erosion, with breaking down the rocks at the surface into smaller pieces. And because the igneous rock from this lava flow is a harder, stronger rock, it acts as a protective layer on the rocks below it. So what we end up with in this final image here is a lava-capped mesa that is not a volcano, because if you look to the left of the mesa, you can see where that fissure was coming up. That long linear feature there, that was our fissure. This was where magma reached the surface. So it is not over a vent, and therefore our hill with the lava rock on top is not a volcano. Okay, so again, lava erupts from a vent or a fissure. You get erosion around the lava flow. The fissure location is marked by a dike. So a dike is a vertical sheet of moving lava. In this case, it has solidified. Eventually, that forms a flat-top mesa, and it is a hill with lava on top, but it is not a volcano because it is not over the vent. Okay, here is an example of a hill that is not a volcano. The dark layer on top is the lava flow, and it is on top of these layered sedimentary rocks below that are softer. Types of volcanoes. There are many types of volcanoes, and we are going to familiarize ourselves with just a handful of them. Okay, the first one we're going to look at is called a scoria cone. It is also called a cinder cone. It is usually basaltic, meaning a very mafic rock. It's made out of rocks like those in Hawaii. They're very dark colored, made of the same stuff that the oceanic crust is. They can be several hundred meters high. And so on the scale of things, these are relatively small volcanoes. Okay, scoria or cinder cones are relatively small, and you can tell that by looking at these images because the vent size looks pretty big relative to the slope there. Okay, and as we look at some of the other images, you'll get a better idea of what I mean. But just looking at the photograph and trying to get an idea of the scale, you can see at the base of the hill there are some bushes. Okay, and so if you can see, maybe that bush is 5 feet tall. So maybe in this case, maybe it's 50 feet maximum. Not very tall. All right, our next one is the shield volcano. Shield volcanoes are big, broad mountains that form from repeated low viscosity flows. Big, broad mountains that form from repeated low viscosity lava flows. So they usually have gentle slopes. They're not very steep. They're usually basaltic. Again, just like the scoria cone, basaltic meaning made of the same stuff as the oceanic crust. And size range from a kilometer across to just huge mountains. Okay, and so the image here is of a shield volcano in Iceland, and this is enormous. We're very far away from this feature, and you can tell that it reaches up very high because we've got snow-capped, and it's just enormous. Okay, but if you were looking at this and driving around, you might not even notice that as a volcano, because usually we think of volcanoes as these very steep, sloped mountains, but in this case, a shield volcano is very gentle. It got its name because it looks like a Roman shield that's on its side. And I have some videos here, so if you want to check out a video of a scoria cone erupting, there's one there, and the same goes for the shield volcano. Our next type of volcano is a composite volcano. Another name for the composite volcano is the stratovolcano. S-T-R-A-T-O volcano. These are big mountains, often snow-capped, and they form alternating episodes of lava flow and cinder ejections. So cinder ejections meaning the volcano sort of sputtering and spitting out bits of rock and ash. So it alternates between lava flows and sputtering out sort of loose material. It's very symmetrical in shape. It has interlayered lava flows, pyroclastic deposits, and mud flows. The type of rock that typically forms a composite volcano is mostly andesite, but it also contains both felsic and mafic rocks. So I'll explain that in just a minute on how to tell the difference between felsic and mafic rocks. I've hinted at it in previous lectures. Now we're going to go in a little more depth. So the composite volcano is the most explosive. It's going to be very tall. If we look at this image, the photo of it, this is of a volcano in Ecuador, and you can see these very huge trees at the base just look like ants compared to this volcano. So again, the shape is going to be a cone shape, but to distinguish between the cinder cone and the composite volcano, the cinder cone is far larger, and so we can see that the vent looks much smaller on the volcano, the composite volcano, relative to its slope because it's so much taller. Another type is the volcanic dome. It is dome-shaped, obviously. It is solidified lava with volcanic ash and rock fragments. It is very viscous, usually felsic or intermediate magma. So very viscous meaning it's extremely thick. It's very difficult for it to move and to flow. Okay, so if I wanted to summarize a volcanic dome, I would say it forms from high viscosity lava, and it's so sticky it doesn't go very far. Also, domes can be very unstable. So while a dome is building, it's not so much trouble. It's once it collapses that it becomes a hazard. Okay, but on its own, the actual formation of the dome just tells you that the volcano is active, but until it collapses, we're all in good shape. Okay, and so I've got a video here of a composite volcano erupting and a really cool time-lapse video of a volcanic dome forming. The next type of volcano we're going to look at is a fissure. And so these typically form flood basalts. So in your notes this says flood basalts. They form from cracks or fissures that allow magma to flow out onto the surface in large quantities. So flood basalts form from cracks or fissures that allow magma to flow out onto the surface in large quantities. So there's no hill, there's no big mountain, there's not even really a crater. It's just a crack in the ground where lava is being erupted. And the type of eruption that you usually get at a fissure is a basalt flow. Okay, I realize you don't have this next image in your notes, but this is a caldera. And just briefly, a caldera is a volcano-related topographic depression. So that just means it's a hole in the ground, basically. It erupts a huge volume of magma, mostly as volcanic ash, and you get rhyolitic domes that build inside the caldera after eruption. So what that means is rhyolite is just a felsic rock, a felsic igneous rock that forms basically just on continental crust. So when we have rhyolitic domes, that just means volcanic domes made of rhyolite. So calderas are very important. I'm sorry I don't have the image on your notes, but I have some cool videos, one of a fissure in Hawaii, and just to be really clear, the video link for the caldera is a simulation. It's from the movie Super Volcano that was done by National Geographic. it is a really cool movie and a great simulation of what could happen at Yellowstone. I don't want to freak anybody out. Yellowstone has not erupted and blown a big hole in the U.S. yet.